Okay, so this is video number 3 of 5 on graph traversal for AQA Computer Science A-Level. If you are not doing A-Level, then this will not necessarily be what you need, but it might be useful, who knows. And if you haven't watched videos 1 and 2, at the very least consider looking at them. 1 is a quick intro, and 2 is going through the breadth first search in quite a lot of detail. This one, going through the depth first search. And a quick recap, a quick reminder, the idea of the depth first search is that we start at a particular node and we just head off in a direction following some rules until we hit a dead end. And if we hit a dead end, we stop and we go back until we can go somewhere else. And we just head off until, following this set of rules, we eventually end up at our destination. And if the route I took seems a bit arbitrary, watch the video number 1 because you'll see the algorithm behind what I've done there. Yeah, that's the idea of the depth first search. Now, this little area down here, where I got stuck at a dead end, what I did was I went to node number 20, then I went to node number 13, then I went to node number 10, and then because I was stuck, I scratched that off, and instead went from 20 to 9. Now, you might recognize that as being an example of a stack. And to implement the depth first search algorithm, we do use a stack in order to achieve that. So let's have a look at this somewhat scary page with lots of things going on and see what we've got. Now, you might recognize this graph in the bottom right if you've watched video 2, because it's the same graph. This time, instead of an adjacency list, I'm going to start by writing out an adjacency matrix. And an adjacency matrix is a way of representing the graph. We can actually do that storing the weights. We don't actually need the weights for this, but it's a good example. So from node 1 to node 2 is a weight of 7. From node 1 to node 3 is a weight of 9. 1 to 6 is 14. And 1 to 4, 1 to 5, you can't do those, they're 0. Same thing for node 2. 2 goes 10 steps to get to node 3, 15 steps to get to node 4. You can't get to 5, and you can't get to 6. Node 3 to 2 is 10. 3 to 4 is 11. 3 to 5 you can't do, and 3 to 6 is 2. 4 to 2 is 15. 4 to 3 is 11. 4 to 5 is 6. 4 to 6 is impossible. 5 to 2 you can't do. 5 to 3 you can't do. 5 to 4 is 6. 5 to 5 is impossible. 5 to 6 is 9. And then finally, apologies for the mess down here, 6 to 2 is impossible anyway. 6 to 3 is 2. 6 to 4, nope. 6 to 5 is 9. And 6 to 6 is impossible. If you've not come across these before, or as a quick bit of revision, with an adjacency matrix, you can never go from yourself to yourself. So all the zeros down this diagonal line, because you can't go from 3 to 3. And then on an undirected graph, a graph without one-way streets, the adjacency matrix should be symmetrical. So from here, I've got to the right 1102, and if I go down 1102. From here, I've got 9 and 9. Here, I've got 790014, 790014. And that's because 2 to 3 is the same as 3 to 2. If it's a directed graph, it'll be slightly different. But again, this video is really about that. So just a quick bit of recap from, hopefully, previous learning that you've done. Then got this algorithm here, which frankly, I'm going to skip over. It's a little bit awkward. It's useful, so feel free to pause the video, have a look, see if you can fathom it out. What it does is it turns that adjacency matrix into an adjacency list by following these steps. I won't bore you with them right now, but it is worth having a look at. It is, again, it's from a past paper, so it is worth seeing. But what we've got is 1 is adjacent to 2 and 3 and 6. 2 is adjacent to 1 and 3 and 4. 3 is adjacent to 1, 2, 4 and 6. 4 is adjacent to 2, 3 and 5. 5 is adjacent to 4 and 6. 6 is adjacent to 1 and 3 and 5. There we go. So what do we do with that? Well, here is, again, from an AQA A-level paper, the code for the depth first search according to their implementation. There are other implementations, but this is the one from that exam. And as before, the variable name's not very helpful, but T is target, S is stack, and V is the node that we are starting from this time. So we're going to start from 1 and try and get to 5. We're going to pass in V and T, 1 to 5. Then stack S is empty, so I'll just mark that off. Discovered is false, all the discovered are false. So I'll write those in. And then we're going to push V onto the stack. So take the stack, push onto it, the thing in the brackets is V, so 1 is going to go on the stack. It's the only thing on the stack, so it doesn't really matter where you write it, it's on there. And as before in the previous video, use your finger to point to where you're up to. At the moment, I'm crossing these off because I know I'll only do them once. Once we're into the loop, I can't do that. So, while S is not empty, while the stack's not empty, and V is not equal to T, V is not equal to T, that's fine. So, pop the stack, which means that will be empty, and put it into V. Now, that's a very weird couple of steps, it looks like. I've taken 1 here, put it in the stack. I've then taken it out of the stack and put it back there again. Now, that does seem odd, I agree, but the idea is we start off this exercise knowing that we're looking at node number 1, and I've just realized that's going to make a mess of the code underneath. Oh, it doesn't, it just looks ugly. But we're starting at node number 1, we're looking around, see what we can see. So we put it in the stack because that's our starting point. So it seems odd, but trust me, it does work. So pop it off. Now, if not discovered V, so if discovered V is false, and discovered V is false, so set it to true. And then for each vertex U which is adjacent to V that is not in S. It's even more of a mouthful than in the last algorithm. So we're going to write these in U. But what are we going to write in U? We're going to write in the nodes that are adjacent to V. So that's 2, 3, 6. But only if they're not already in the stack. So we've added an extra level of complexity there. This is not very straightforward code. If you're going to write this in Java or Python or VB or whatever, then you would need to write much more complex code than that. But that's fine. We can just kind of use it as it is and apply a bit of English common sense to it rather than writing all the extra code there. So all the nodes that are adjacent to V that are not in S. Well, there's nothing in S at the minute anyway, so it's going to be 2, 3, 6. So U will be 2. What do we do? If it's not discovered, then push it. We'll push it onto the stack. That's it. Really, really short, really simple. End 4, go around and get the next one. Next value of U is going to be 3. And then if not discovered, 3 is not being discovered, so push that onto the stack, push it onto the top. And then go around again, get the next value, which is 6. Just in case it's not clear, I'm getting these from down here on the left, my adjacency list. And again, if it's not been discovered yet, and it hasn't, push it onto the stack. 2, 3, 6, there we go. That's the end of all those, and we've done every adjacent node. That's the end of the if, end of the while, so back around the while loop. And as long as the stack isn't empty, and V is not the target, do the next one. So we pop off the top of the stack, remember, and put that in V. So get rid of the 6 and put it in V. Now, I said never go left in the previous video. I'm doing these two at the same time. So I think it's okay to do those at the same time. Okay, you take the 6 from there and put it there. It's one operation. It's one line of code. I think I'll get away. So pop that off. And then as long as 6 hasn't been discovered, and it hasn't, then set it to true. So this time discovered actually means interrogated. It doesn't mean have we ever seen it. It means have we interrogated that node. And now we have started to interrogate that node. So we go to each adjacent node. So we want each vertex U that is adjacent to V that is not in S. So what's adjacent to V? It's 1, 3, 5. What's already in the stack? 3, so we can skip that one already. So we just want 1 and 5. So we'll look at 1 first. If not discovered, well, 1 has been discovered. So we'll skip that if statement. Go around and get the next one. Next one is 5. And that one hasn't been discovered. So we'll push that onto the stack. 2, 3, and 5. Remember, it goes onto the top of the stack. So that's done. We've run out of adjacent nodes, so we've done 1 and 5. So end while, up around the while loop again. While the stack is not empty, the stack is definitely not empty. And v is not equal to t. V is currently 6. That is not equal to t, the target. So pop the next thing off the top of the stack, which is 5. So 2 and 3 are left, and put that in v. So v is the result of popping the stack. So if not discovered v, and v is not discovered, then set it to true. So we can label 5 now as having been interrogated. And for each vertex u that is adjacent to v and not in S. What's adjacent to 5? It's 4 and 6, and neither of those are in the stack. So we'll do 4 first. And if it's not been discovered, it's not been discovered. Oops, put that in the wrong place. It's not been discovered, and it's not been discovered. Then push it onto the stack. So 2, 3, and 4. Then get the next adjacent node, which is 6. And if that's not been discovered, well, 6 has been discovered. So we don't need to push it. So that's done. End of the for loop, end of the if statement, end of the while loop, back around again. While S is not empty, the stack is not empty. And V is not equal to T. Well, V is equal to T because V is 5, T is 5, they match, all sorted. So actually, skip to the end of the while loop, end of the procedure, and we're finished. There is our trace table. The really important bit is I didn't go, haha, I found node 5, I stopped. Because there's a whole lot of things we do after that, because the algorithm says to. Until the algorithm says stop, you've got to keep going. Because if you just stop there, you're going to lose marks for this column, you're going to lose marks for this column. We don't want that to happen. Okay, so that's the idea. Now that one was a lot quicker than doing the breadth first search. And this is going to be very messy when I do this, because it's already full of scribbles. What did we do? We started at node number 1. We looked at all the adjacent nodes, which were 2 and 3 and 6, and we put those into the stack. But then we took the last one, and we just went, well, where can we go from there? Remember we said look at all the adjacent nodes that aren't already in the stack. 3 was already in the stack, so we ignored it. 1 wasn't, but we had discovered it, so we ignored that. So we added 5 to the stack. At this point, the stack was 2, 3, and 5. 2, 3, and 5. Up here. Then we say, right, well, we'll just continue. We'll interrogate node number 5. Take that off the stack. What's adjacent? We've now found node number 4. So we'll add that to the stack, and the stack is now 2, 3, and 4. But then actually, we stop and we realise when we've finished interrogating node 5, we've actually found our target really quickly. So rather than spreading out like we did for the breadth first search, we've managed to get there quite quickly, and we've managed to find a route out. It might or might not be the quickest route out. It actually is, but we don't know that. The point is we found the route quickly, and that's a real advantage. So going back to video number 1, if I just go back on here we go. You've got your breadth first search and your depth first search. You see all my scribbles from previous videos, but your breadth first search, remember, you start at your start node and you spread out like a virus, going like this, looking at everything that's 2 nodes apart, then 3 nodes apart, and spreading out. That can take you a long time, but it will find you the best route. Whereas your depth first search, which is down here, you just head off in one direction until you hit a dead end and go back again using the stack data structure. You will find a route typically quicker than if you've done breadth first search, but you won't find the quickest route most likely. Okay? And as I said with the last one, if you want to do a bit of practice, here is, just take a screenshot, pause the video, take a screenshot. There's another graph to have a go at. And there's the algorithm, take another screenshot, have a go at the algorithm. And then there's a third one to have a go at as well. Again, just pause the video, take a screenshot, and then have a go at filling those in. Once again, it's A to F rather than 1 to 6. I always set these for my students as get from A to E, 1 to 5. But try mixing it up, try getting from C to A, F to A, and see if you can find different routes using breadth first and depth first until you're confident. Two more videos to go, and we're going to have a look at Dijkstra's algorithm in the next two, which is a whole different way of approaching graph traversal. Then that's all three standard algorithms completed, and hopefully a bit of practice thrown in there so you're fairly well prepared. Best of luck.